Hi, I'm Paul Duckworth from the Oxford Robotics Institute at the University of Oxford, and I'll be presenting our joint work on time-bounded mission plannings in time-varying domains. In this paper, we're interested in mission planning over time-varying environments, where we posit that the environment dynamics affect the robot's action outcomes. For example, on the right here, we show real-world ocean currents data that may reasonably affect the velocity of an AUV as it traverses the region to perform a mission. We develop a method for time-bounded mission planning in such scenarios. Our contributions are that we formulate time-bounded decision-making problems into a semi-Markov decision process, where each action has an a priori unknown duration that is affected by the environment dynamics. We incorporate a time-varying transition model that appropriately manages environment uncertainty into Monte Carlo tree search. This allows us to satisfy time-bounded missions specified in co-safe linear temporal logic over time-varying environments. Briefly, I'll go over the steps required to achieve our time-varying semi-MDP formulation. First, we specify our mission, phi, in co-safe LTL, such as eventually reach the goal state G and a time-bound T. Second, we require a factorized state space. Here we have known state features and latent state features. That is, those that require estimating and a belief is maintained over them. Third, we specify a flexible function approximator to maintain this belief that maps from the known state features to the latent state features for any future states the robot may arrive at. Where here we have employed a Gaussian process that is updated with observations gathered online as the robot moves through the environment. Fourth, we extend an MDP with an action duration distribution delta. This now is dependent on the time-varying belief distribution over the latent state features. Finally, we perform MCTS from the robot's current state, where each search node is extended to maintain not only the known state, but also the time the node is reached during planning and the mission satisfaction information. I'll quickly demonstrate the extensions we made to the MCTS search nodes and the sampling procedure. Here I show the root node that maintains the initial known state. For example, xy could be 0, 0, the initial time, t equals 0, and the initial belief over the latent state feature, SE, and the initial state of the finite state automata representing the mission specification. During UCT planning, the robot selects an action using UCT and a resultant known state based on the transition model. We then compute the posterior distribution over the latent state feature at that known state value. We then sample an action duration from the delta distribution that specifically maintains the full posterior belief over the latent state feature at the current time. We update the finite state automata state x according to the newly reached known state xk. This concludes the generation of our new search node n prime. This is repeated a fixed number of iterations, and a policy is extracted. We use a rollout heuristic, and a reward is backpropagated if any trial reaches the goal state within the time-bound t. In summary, we formulate a time-varying planning problem into a semi-MDP framework with a priori unknown action durations. We train a spatio-temporal Gaussian process to maintain a belief over the latent state features at future locations and times, where the belief posterior is used throughout the MCTS search for an optimal policy in timed missions. We show improved mission performance over a number of real-world Atlantic Ocean regions for missions specified with multiple goal states. Thank you for listening.